Great.
Tremendous.
Professor Das, should we begin?
Yes.
Okay, thank you.
So, okay, so my name is Bhanu Das. I'm the director of the Center for Quantum Engineering Research and Education. It's my privilege to introduce today's speaker, Professor Artur Ekert, who is currently affiliated with Oxford University, the Center for Quantum Technologies in Singapore. He was the founding director of that center, and he's an adjunct professor currently at Okinawa Institute for Science and Technology. Professor Ekert is one of the pioneers of quantum information science. And as many of you know, I mean, he has made many profound contributions to the entire field of quantum information. And the contributions are so numerous that it's impossible to mention in a simple introduction. However, I would like to say that the work that he did on quantum cryptography was undoubtedly groundbreaking, And his paper based on that work, which I think he did as part of his doctoral thesis, which is quantum cryptography based on Bell's inequalities, has been very, very influential. And it's one of the most cited papers in quantum information science, probably in physics. So I can say a lot of other things, but about his contributions to this field. But I will now request him to speak. And before that, I would like to say that he is also, among many other things, the chair of a scientific advisory board. That is the chair of the scientific advisory board of our Center for Quantum Engineering. And I've personally benefited from his advice and his deep insights into this field. And I'm sure many of you will learn a lot from his talk and get a sense of the importance of this year's Nobel Prize for Physics. And I think his contributions in advancing Bell's inequalities, I think, will be evident from his talk. Okay, I would now like to request Professor Ekert to give his talk.
Well, thank you, Banu. Thank you very much for your kind words and your introduction. And I feel humbled, actually, by all those nice words that you said. And thank you for having me. I'm going to, let me try to share the screen again. Okay. Right. So my talk today will be actually probably more popular in nature than many of you may anticipated. It's not the point to go into nitty-gritty details of mathematics or even sort of subtle aspects of physics, but just I want to tell you a story. And as Banu asked me to talk about the Nobel Prize that was awarded to John Clauser, Alain Aspect, and Anton Zeilinger earlier this year. So my narrative is essentially about this prize and how their work that started as mostly was driven by curiosity, at some point became very important from the sort of a practical point of view, which sort of brings the moral to the story, which is that even though you may be doing something that is very fundamental, something that is almost philosophical, at the end of the day, you never know. This work can be used for something that is very practical eventually. And cryptography, which I mentioned in my talk, is a good example. So for years, people thought that some aspects of number theory will be so pure, mathematically speaking, that they will never be tainted by any applications. And here we are today, where we use number theory for data security. Well, anyway, so my talk is about essentially about Bell inequalities. And I would like to tell you a story how research focus evolved from curiosity-driven research to something that has, some potential practical applications in data security. So hence the title, Bell inequalities from curiosity to security. So the story starts when I was preparing this talk, actually earlier today, in fact. I was thinking, how to structure my narrative, and then I thought maybe it's just as everything, when you have European roots, it always goes to ancient Greece and ancient Rome. So here we are. Let me start with the notion of randomness. So when you think about when you hear that something is random, what does it really mean? How do you visualize? How do you conceptualize the concept of randomness? is randomness, and here we are trying to make a clear distinction, is randomness something that is out there, something objective, something inherent, or is it something that we perceive as random? Maybe there's no randomness out there, but we perceive something as random because we lack knowledge about how things happen. So those two different sort of schools of looking at randomness as something objective and something subjective essentially go back to ancient Greece, where you have, and you can see here on my screen, two philosophers. One is Epicurus, the other one is Democritus. And they both express their views on randomness and taking somewhat different, maybe opposing position. So Epicurus certainly thought that it is objective, it is out there. He says that atoms, swerve at random along their path. Whereas Democritus actually thought that it's subjective, it's that atoms are there, and they follow predetermined path. And if there's any randomness, that just comes from the fact that we lack information about the system. And, the concept of whether things out there can be random or not, whether they are predetermined or not, entered all kind of philosophical and even theological debates. When you think about it, it is actually an important thing that there's this dilemma of determinism when you, whether you go into theology or you start thinking about ethics, and so because indeed, if it is the case that everything is predetermined, if everything, if our actions are caused entirely by past events, then how can we be responsible for anything that we do, right? So it's already written out there. What we are, it'll be quite clear what I'm going to, what will happen, say 5 minutes from now or at some point in the future, and all my actions are predetermined, and I may not have therefore free will. So it's just, I'm not saying actually that determinism implies lack of free will. In fact, there are ways to analyze the notion of the free will or unpredictability in the context of deterministic scenarios, but I'm not going into this. So essentially, just this slide is telling us that the whole concept has a history, that people thought about it, that it was important for all kinds of different reasons. So people were fascinated by the fact, are we deterministic in a sense? The whole world is deterministic. It just follows a certain predetermined trajectory, and or perhaps there is inherent randomness out there. It's difficult, we are so much, how shall I put it? We are so much into thinking about causes and have some kind of perception of the world that we kind of understand. We understand the dynamics of the world. We have a certain intuition of what will happen when we do this and that. So thinking in terms of causes and effects gives us this concept that everything has a history, right? Everything happens for a reason. So if we just were to use a simplistic space-time diagrams, which I sort of presented here, it's difficult to think about truly random event, because objectively random event would have no history. So it's like a timeline that starts at some point and there's no history there. One can, of course, put a twist on this. One can try to consider more outlandish scenario in physics, where you may have a backward and forward propagation, and that could give a reason to some sort of randomness. But essentially, it's very difficult to visualize, to conceptualize randomness per se as an objective phenomenon. It's much easier for us to accept that this is something that happens because we cannot calculate something, the system is too complex, we don't know, we cannot make predictions, and we perceive certain things as random. So like a toss of the coin, we perceive it as a random because there are so many factors involved, but we do know that as a matter of fact, it's perfectly predictable, perfectly deterministic system. So, and even though this concept of inherent randomness existed and was discussed and has been discussed for years and for ages in various contexts, it became even more important in the context of quantum theory. And when quantum theory was born by a sequence of trials and errors and guesses, as usual, whenever we sort of apply our creative mind to create something new and propose a new theory, it was clear that the best we could do, or the scientists could do at the time, is to make statistical predictions. And the question remained whether this is really the best you can do. So is a physical theory that gives you probabilities, assign probabilities to different outcomes in your experiment, but can never tell you for sure what's going to happen, well, except maybe special cases. Is this the end of the story? Is this something that is the best we can really have? And because it was a bit bizarre that if we make identical preparations and identical measurements, the outcomes can be different, right? So that's and quantum theory tells you that this outcome may happen with such and such probability and some other probability. And here actually people divided people sort of, if we were to classify different views, maybe there would be like 2 or maybe 3 different views. So there would be those like Albert Einstein who said, well, it's provisional, it's not complete. There is a real underlying real thing, the real theory that once we know it, will just tell us exactly what's going to happen. There's no way if there's, higher end entity like a god, the god plays die. And so it has to be predictable. It has to be maybe complex, maybe extremely complicated, maybe difficult, or for all practical purposes, even impossible to make predictions, but nonetheless, the essence is such as deterministic. So that was one view. Quantum theory as a provisional concept, as something that is not complete. On the other side, of course, there were people who thought, well, maybe it's the best we can get. Maybe we have to live with this randomness. Maybe it is inherent somewhere there. And of course, there's a third group. They could say, well, I couldn't care less. And actually, probably that was the largest group. Most hardcore physicists could hardly just waste their time on philosophical debates of that time. Say, as long as it works, right? I can make predictions as long as it just works as designed, so that's fine. So that's a very instrumental approach. Einstein was clearly pushing for explanations. He was trying to understand deeper, what is it really about? And here we can see the first paper that was sort of articulated the whole thing more than anything else. That was his 1935 paper, written together with Podolsky and Rosen. It's known as the EPR paper, where he really questions whether quantum mechanical description of physical reality is complete. And and he says, well, if you take quantum theory seriously, there are consequences, and those consequences are weird. And one of them is that there may be a difficulty to even assign a value to certain observable properties. So the questions of existence of the so-called element of reality, to which we will come later. So here is Einstein posing this question, and then basically considered as a philosophical question, but a very deep and profound question, right? And would it be then possible to have a test that would tell us whether quantum theory is complete? It's all we can have. or there is some hidden structure, underlying structure, which can help us to make better predictions, sharper predictions, and provide maybe some insights and better explanations. So here enter Jones Bell, and we are moving from 1935, and so like 30 years later or so, there's John Bell, whose job was essentially he was a physicist from Northern Ireland, from Belfast, worked in Switzerland. His day job was to design better accelerator for high energy physics experiments. But after hours, he was basically playing with the foundations of quantum theory. And so which is, to all students out there and to all those people who have boring day job, there's sometimes it may happen that you are known for not what you were supposed to be doing, but what you did after hours. So John Bell is a good example of this. So here's a John Bell who actually says, well, if you take Einstein consideration, I can turn it into a testable proposition. So in other words, the concept where there is underlying structure that satisfies certain conditions, so called the local hidden variable theory, which essentially says there is underlying structure, then properties are well defined. If you see something that you can measure, it has numerical values, and also objects carry those things, and if they influence any other objects, so that has to propagate, this influence propagates with a, say, speed of light, so it doesn't happen instantaneously. So he made a few reasonable assumptions what this underlying physical hidden structure might be, a la Einstein, and showed that it actually has it has consequences that can be falsified. So it's just you can set up an experiment that would actually tell you which one is the case. And this is actually a very, very simple explanation of the Bell inequalities, not in the way that Bell did, but sort of generations after generation, we simplified it to the basic minimum, and here we can see the basic minimum. So if you want to know what the Bell inequalities are about, so here is one version of the Bell inequalities known as a CHSH inequality, from Clauser, Holt, Shimony, and Holst, Shimony, and Mike Horn. Right. So let me explain this diagram here. So here you have, if you haven't seen it before, probably many of you actually saw it, but if you haven't seen it before, so here's like one slide crash course in Bell inequalities. So it represents an experiment which you can set up. So imagine that there is a source somewhere that emits two particles. We will later refer to those particles being entangled, but at the moment we are not making any statements related to quantum theory. In fact, Bell inequalities have nothing to do with quantum theory. It's a statement about correlations. So imagine that we have two particles that have certain properties that we can measure. So you may think about polarization as and the two particles being two photons. So let's use photons and polarization. So one particle that comes from the source goes to a physicist called Alice, and another particle goes to a physicist called Bob. And Alice has a choice to measure two different polarizations of incoming photon. For each incoming photon, she will choose either A1, so a type of polarization A1, or another type of polarization A2. So it could be, for example, measuring vertical or horizontal polarization, or any other. So the same for Bob, who receives incoming photon and choose to measure either B1 or B2. We now assume that if there is an underlying physical explanation, sort of the deterministic structure, then A1, A2, and B1 and B2, even though we may not be able to measure A1 and A2 at the same time. We choose only one of them, but nonetheless, we assume that they just have values, that those photons carry predetermined values associated with every possible polarization that you can imagine. So you may think about A1, A2, and B1 and B2 as a binary random variables with values +1 and -1 in the unit of H bar, right? So if you have such random variables as A1, A2, B1, B2, and they do take values, then you can construct another random variable S, which is a simple linear combination of A1, A2, B1, and B2. As you can see from the definition of S here, that it can only take two values. It can be either +2 or -2. And the reason for that is that one of the two terms in the brackets, B1 plus B2 or B1 minus B2, has to be equal to 0, and the other one, of course, will be ±2. So that means that S takes two values, +2 or -2. And if you run this experiment many times, so sometimes the value will be +2, sometimes it will be -2. And if you can measure S, which you can, be statistically speaking, because you can measure correlations between A1 B1, A1 B2, and A2 B1 and A2 B2, then you can estimate the average value of S. So surely, because it takes the average value is somewhere between the two extreme values, -2 and 2. So the average value will be falling into the interval between -2 and 2. So that's it, This is this is CHSH inequality. And there's a tacit assumption, of course, here that those values do exist. And that's a statement about correlations. It's such a trivial statement, mathematically speaking, that you would expect all possible correlations to satisfy this inequality. So what is interesting is that quantum theory predicts that this inequality may be violated, that S may jump out, that the average value of S may jump outside this interval. In fact, it can be as large as 2 square root of 2. So that then, of course, this is a theoretical predictions, and here we come, and we have our first hero, John Clauser, who was a young postdoc at the time at Berkeley, and it's year 1972. So again, 10 years later, essentially, he writes to John Bell, asks for details, and is sort of mildly encouraged by John Bell to test those Bell inequalities, and certainly not so mildly discouraged by his supervisor not to waste his time on something that is philosophical. So you see, the whole field has already this kind of a philosophical context, philosophical flavor that is not up to the taste of many physicists involved. So hardcore physicists, again, are just about predictions. Don't think about any mumbo jumbo, who cares? And so here, the postdocs have good ideas. So again, to those of you who are postdocs, and some, the message is a good message, a rebellious message is, sometimes it's okay to go against advice of your supervisor and do what you think is interesting and what is right. So John Clauser was you can see him here with his experimental setup. So he runs this experiment, he sees the violation of Bell inequalities, he does it with his colleague and I think PhD student Stuart Friedman, and but it's a lousy experiment by modern standards. So the question is, there are many loopholes. If you start analyzing this experiment, then yeah, it does work in a sense. It shows the violation of Bell inequalities, but there are many buts. You can ask, what about detector? Is it efficient enough? Have you been switching those detectors? Can somehow detectors communicate it? So you come up with all kind of possible conspiracy theories, right? So that nature can play on this poor John Clauser. And there are a number of them. And so it's quite clear that this is not yet the most convincing statement. But essentially, nobody cares about this experiment. It's hardly noticed. And then here's our second hero, Alain Aspect, who, again, 10 years later, is excited, talks to John Bell about it, gets fascinated by the whole thing, and is driven by this curiosity. Here he wants to know, is there really something like inherent randomness out there? So Alain comes up with an experiment that appeals to many of us. I was a student at the time, vaguely remember that I got to read at some point a thesis of Alain where all those things were nicely explained. And somehow that experiment, for some reason, it was maybe more, it was just at least known to more people. People talk about it. It was noticed, but not to the extent that it created any excitement in the community. Just think about it. Here we are, sort of a rather convincing experiment. Sure, there's still loopholes there, but still, nonetheless, very convincing experiment, which tells you something very deep and profound about the nature of reality. And as it was put by one of the writers who wrote about it, all that evoked was a collective shrug. People said, yeah, we know that the quantum theory works, right? So why would you bother? And so that, that seems like everyone at the time was convinced that quantum theory works, and then that the Bell inequality should be violated. Maybe not so many people thought that it has some interesting philosophical consequences. And of course, I should add perhaps here that seeing the violation of Bell inequalities, if you go into more subtle analysis, doesn't necessarily tell you that there is inherent randomness in nature. It may actually tell you that everything is predetermined, including the experimental setups in which you have to choose randomly whether you are measuring A1, A2, B1, B2. So we call it a superdeterminism. So that's still possible. But if you sort of like reasonable and say, well, maybe it is the case that we do have free will, can make random choices and run those experiments. So that would indicate that there is something unusual, and that requires at least to revise our notion of underlying structural reality. And how we are going to do that is another story. So people may just, there are volumes written and zillions of discussions. What the violation of Bell inequality does really tell us, you can take here different views. It certainly tells us that quantum theory is the best we can have at the moment. Modular maybe super determinism, but how we then interpret the whole thing, it's an interesting thing. There's people in the many world interpretation, for example, will tell, well, it's there is a deterministic kind of evolution across the multiverse, and then when we slice this multiverse, we may just perceive randomness, and so on and so forth. So there is lots of further discussion, but nonetheless, at this point, I think most physicists just acknowledge the fact that the Bell inequalities are violated as predicted by quantum theory, therefore not so surprising. Most physicists do not go into philosophical debates, just leave it to philosophers and just carry on doing kind of practical things. And here, so this kind of ends the story, but not quite. If you're really curious, if you really want to go into subtle details, you still may question those experiments. You may say, okay, there are loopholes here. There are problems with detections. There are problems with random choices, how fast you make random choices, and so on and so forth. And but there was not really any drive to do anything about those loopholes, simply because why would you bother? Just you're convinced that things are done, even though, strictly speaking, it would be just nice to close all those loopholes. So here is something that just brings me to the key sort of message that I want to convey here. So somehow, in the most surprising and unbelievable way, another field related to data security, cryptography, helped people who are interested in the foundations to somehow complete the program. And so this helping hand was offered by quantum cryptography. And so as you can see, I'm showing here the merge of curiosity-driven research in the foundations, which you can see at the top line, from Einstein to Bell to John Clauser to Alain Aspect. So those people really were going against any trends. Really, honestly, that it required, especially, forget about Einstein. Einstein was well established, and John Bell had his day job. But John Clauser and Alain Aspect, they had to struggle they went against establishment, against the trend, against anything that they were supposed to be doing. And neither of them at the time got any recognition for what they achieved. Most people acknowledge the fact that those experiments were important, but not more than that. So there's the plot that you see on the top right corner. It's just a simple Google statistical indicator how often the word of CHSH inequality or quantum entanglement appeared in literature over time. And you can see that around, so even though you went through all those fantastic experiments in the 70s and 80s, it just hardly picks up, It's only in the 90s it picks up rapidly, especially quantum entanglement. And why is that so? And the reason is that a fusion happens. So on one hand, we have the field of quantum cryptography, quantum computation, quantum communication, and where those quantum phenomena start playing an important role and they're used for computation. But in particular, in the context of Bell inequalities, it turns out that the Bell test can be used for testing and eavesdropping in a communication scenario. So it can be used for something that is called quantum key distribution. So I wrote about it in '91 and didn't actually think much about it, to be honest. I just noticed this connection, and then I was completely taken by surprise that it sort of took off and acquired life of its own, and this paper became so popular later. So those people who came later, Anton Zeilinger included, although Anton did all kinds of other interesting and fantastic experiments, but let me mention that Roland Hansson, Nicolas Gisin, Jianwei Pan, and the two guys I was working with, John Raritt and Paul Tapster, that you see at the bottom on the left-hand side, they actually already were working on Bell inequalities, but their narrative was changed at the time. So the narrative was, okay, we are not only just doing curiosity-driven research, we can use this stuff to guarantee the ultimate security of messages. So we can, by doing this, we can exclude any sort of sign of eavesdropping from the communication line. So beautiful experiments, but somehow the narrative changes. There's still, admission, especially Anton always likes to stress it's basic research what is driving him, and this is indeed the case. But then you have also a benefit of saying that, but this is also important. This has a practical implications, and in particular, the loopholes have to be fixed. So that gives sort of like a lifeline to the curiosity-driven research, to philosophers, and saying that your tools actually are important. We are going to use them for security, but we also give you motivation now, because then you have another reason why you should be still carry on and doing this kind of stuff. But we'll come to this in a moment. So just to, I'm not going to talk about what is key distribution, how the quantum crypto works. There will be a few slides that will just sort of like go through very quickly, but essentially what cryptographers were looking for was a way to establish a random sequence of bits in two different locations. Those sequences were supposed to be completely random, supposed to be identical, and supposed to be secret, so known only to Alice and Bob. And then once we can achieve this, once we can distribute this randomness, create this private randomness, private shared randomness in different locations, we can use a system that is called one-time pad, which essentially guarantees perfect security, just provable security that no other system can guarantee. So it was not clear how to do it, and until maybe there were some other approaches. So that was mostly due to Charlie Bennett and Gilles Brassard that use quantum phenomena, but not quantum entanglement for the purpose of generating such a secure key. And my work was completely independent from that. I didn't know about their work. But going back to the paper that you saw, the Einstein paper, I was interested very much in the foundations, and I read this paper, and what attracted my attention was this one paragraph where Einstein is trying to define a physical element of physical reality. So he goes on. Einstein is actually very, very precise and very clear in this paper. I say Einstein, but it's Podolsky and Rosen. So he wrote the paper with them. But it's clear that Einstein has a main voice there, right? It's quite clear that the clarity of presentation is beautiful there. So Einstein just knows that in order to question or show the paradoxical aspects of quantum theory, he has to define all those concepts very carefully. So he defines physical reality or element of physical reality, that something does exist out there, by saying that if without any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. Now, okay, fine. As a physicist, you read it, you think about it, and as a philosopher, you can do the same. But for cryptographer, that is actually something interesting. So I had a background in crypto and applied math. So I was reading this and I think, gosh, this is a way to define perfect eavesdropping, right? So from a physical point of view, what an eavesdropper wants to achieve is to learn the value of a physical quantity that encodes information, 0 or 1, so polarization, for example, without any way disturbing the system. So you can have a passive reading of this information without disturbing it. So that means that definition of an element of reality can be translated into the definition of eavesdropping. But then, I knew that there are scenarios, there are ways that Clauser and Aspect showed that you can have situation where that you cannot attribute an element of physical reality to this physical quantity. So then you say, obviously you start connecting dots and say, hey, how about I use it for the key distribution? So if I see the violation of Bell inequalities, then it tells me that nobody touched those particles. There is no physical reality you can attach there. There's nothing for an eavesdropper to measure. So it's just like a very simple line of reasoning. You say, okay, photons do not carry predetermined values of polarization, because we see this looking at the violation of Bell inequalities. So then the values somehow, however you want to phrase it, they don't exist prior to the measurement. They are not available to anyone, including eavesdropper. So the testing for the Bell inequality, for the violation of Bell inequalities, is essentially testing for eavesdropper. Once you see the violation on a certain subset of your data, you know that those particles were not touched by anyone. You can measure the rest of the sample and get some key out of that because there was no one eavesdropping on it. That's of course, a simplistic thing. Then in order to turn it into a statement about the data security, and then you have to do a little bit of mathematical gymnastics. And but the beautiful thing is, so the thing is that you have to estimate something that is called a smooth mean entropy of the data. So there is a certain figure of merit that tells you how much secure data you can get out of the if you distributed n entangled particles, what is the fraction that you can get that is really carries secure information. So that was important because it was also important to show that it's not, the system should not only work in the extreme cases where you see the maximal violation of the Bell inequalities, but also when there's a partial violation. But of course, then the system also shows, the algorithm also shows that if you go below, with this figure of merit S below 2, that you cannot exclude a possibility of eavesdropping. So therefore you have to just abandon the key distribution and try again. So try to achieve this figure of merit S greater than 2, and from that figure of merit you can just do a bit of mathematics and figure out this entropy that I mentioned. From entropy you do some extracting of the security, and you generate the secret key at the end. The beautiful thing about this was this, in this scenario, that the distribution of the particle can be done by your adversary, by an eavesdropper. So I have to say, looking at this from this perspective was interesting, and I very much wanted to see how practical, how realistic it is. Mathematics was mathematics, but now you want to run Bell inequalities, but with a different narrative. And so what I did, I sided with two colleagues of mine who used to work for something that used to be called DRA, Defense Research Agency in Malvern in Oxford. And I work with John Rarity and Paul Tapster, two amazing guys, two experimentalists who work for this defense establishment. And the funny thing was that they are not supposed to be doing any kind of basic research, but they did. And another amusing fact was that at the time, and even today, the Malvern lab was funded by the Ministry of Defense. Whereas for some purely historical reasons, any research in cryptography is run in a different institution, in different agency called GCHQ, Government Communication Headquarters, and that's funded by a separate, by the Foreign Office. So that like two different ministries funding two different operations, and that was hilarious because at some point, John and Paul had to ask for permission to do this kind of experiments, and we were told, "Oh no, you cannot do crypto experiments. That's Foreign Office, and your defense. If you're not pointing your laser at the tank, you're not doing research, as far as we are concerned." So that was moreover, as soon as they just figured out that they can fund this research, then they just wanted to keep it classified. That was another funny thing, because by that time I sided with Charlie Bennett and Gilles Brassard, and we wrote a popular text about the whole thing in Scientific American. So it required us to bring the Scientific American to the bureaucrats and show it to them and say, look, you cannot possibly classify what is published in Scientific American, right? There may be some technical details that you may want to keep secret, but other than that, it's just, the concept is out there. So there are, all kind of anecdotes, amazing stories, and it was science entangled with life and all kind of interesting adventures. But we did those experiments that show the proof of the principle, it can work. And then the story, I thought, that was kind of over. That's it's fun, it's interesting. Maybe it will be used one day, but not probably in my lifetime. I just forgot about it, wanted to do other things. But at the fundamental level, I was surprised that there was more room to discover things. It turns out, that the Bell inequalities are very rigid in the violation of the Bell inequality. If you see the violation of the Bell inequality, it cannot happen in any other way but by measuring a certain types of entangled particles in a certain way. So that, and it was not my doing, but my colleagues from, many places, and Switzerland, Spain, Singapore, came up with the concept that using essentially exactly the same protocol that I proposed, that they just showed that this also, the system is the so-called device independent, that you don't even have to trust devices that you use. So that's bizarre, right? So it's like you can go to someone and you say, okay, well, I see that you are selling those devices. They have two knobs for positions A1, A2, or B1 and B2, and they click and they generate data, and I can take them to two different locations, and if they can generate data that violate the Bell inequality, I don't really have to know what is inside those devices. I know that they generated data that are secure. So this device independent is a completely mind-boggling thing, and it's just a beautiful application of the Bell inequalities. And so there was never mind history, but that to prove the security of the device independent was actually not an easy thing. If you cannot make any assumptions about the device, that's tough, almost impossible. So you had to make some assumptions, but finally we have the very convincing and beautiful proof, and that we got just a few years ago, about 3 years ago or so, based on something that is called entropy accumulation theorem, called EAT, and that was I like this work a lot. I thought it was a beautiful piece of mathematics, mostly done by a PhD student, Rotem Aron Friedman, a brave woman that you can see here, working together with Renato Rene on the top and Thomas Widig on the left. So that's all proven, and again, never mind. I think that the beautiful thing is that the same year that we got the Nobel Prize for Bell inequalities is the year, just a few months earlier, we saw beautiful experimental verification of the device independent key distribution. So you have experimental quantum key distribution certified by Bell theorem. And so there were 3 groups that published more or less at the same time papers. 2 of them appeared in Nature back to back, and 1 in Physical Review Letters. So there was a group in Oxford, there was a group in Germany, and there was a group in China, but there was international collaboration. And you see, the reason why it was possible to do this kind of experiment was because of quantum crypto. So because of the motivation, but the tools that were developed by people like Clauser, Asper, Zeilinger, and many others were absolutely essential to set up those experiments. And in particular, that what was essential was to close all those loopholes in the Bell inequality kind of scenario, simply because when you deal with nature, you don't take this adversarial scenario. You don't say that nature is really malicious to you. It's very unreasonable to think that nature is cheating on you, say, exploring some kind of loophole in one experiment and exploring another kind of loophole in another experiment. So therefore, most people wouldn't be bothered too much about those loopholes. But in the crypto scenario, it's very important, because your enemy, your eavesdropper, can be malicious and can cheat on you or can explore your weaknesses using this kind of attack in one experiment, another kind of attack in another experiment. So you have to actually close the loopholes. So you see, the requirement for security for the device-independent crypto was absolutely it was pushing the, if you were to just demonstrate those things and prove the security, essentially you're proving you're closing the loopholes in your Bell kind of verification of security. So we ended up with a Nobel to Alain, to Anton, to John Clauser. And I have to say, on a personal note, I never met John Clauser, but I worked with Anton and Alain. So with, in fact, first time I was called a professor was when I was still a PhD student, and Anton invited me to join his team in Innsbruck. And so you can see Anton at the time in his sort of fancy house, actually a beautiful one. I really like that one. It's a pity he moved back to Vienna. I don't know whether he still owns this house, but that was a place we got together every now and then over having a good chat over a good glass of wine and cheese, and talk about life, universe, and everything else. So that was the time where we sort of work on the entanglement swapping that was explicitly mentioned by the Nobel Committee. There was another idea, not related so much to Bell inequalities, but about extending the range of distribution of entanglement. Now, Alain, that you can see on the right-hand side, so he's joking that I look here like his bodyguard. We are just we've known each other for a long time, and I think Alain was my mentor in more than one way, because he was. He kind of recognized the value, the importance of this work when I was a PhD student, and I was trying to present it, and I was a bit scared at first. After one presentation in Paris, a guy with a big mustache comes along and asks all kinds of questions, and then you later discover it's actually quite a fantastic person, nothing to be afraid, with a great predilection for good wine. So you can see us here. Actually, last year we were shortly before Alain got his Nobel Prize, we were in Bordeaux, officially attending a scientific advisory board to a local research center. But after hours, and I keep telling you, sometimes it's more important what you do after hours. We had a great fun tasting good wine with Alain, so this one can, at this point, which is one can say, is that the end of the story? So that we have the fusion of crypto that helped people to do better basic research, but also the experimental tools developed by those people help to set up a new schemes for very secure communication. So is it the end of the story? There will be something else. I think that, of course, there will be always something else. One thing, for example, that is worth looking at is the subtle thing that I only mentioned very briefly, that when you do the testing of the Bell inequality, you have to really, really guarantee that those random choices are truly random. I mean, the choices of what you're going to measure. So it's not only that you generate and you prove randomness in the generation of data in the Bell inequalities, but you also have to have a bit of a randomness, and how genuine that randomness is, and what are the requirement for this randomness when you run the Bell test. It's another story. In fact, you don't require that much, but it's interesting to see how that may work in adversarial and crypto scenario, and so on and so forth. So the end of the story is that there's no end of the story, right? So there is something still interesting to look at, and it's getting more and more subtle. But for now, I think we can conclude that I can conclude by saying that I'm actually really happy that this field finally was recognized by the Nobel Committee, because it brings it to sort of to attention of public, to students, and more young people will go into this field, hopefully, and this will be only good for science and for the field itself. So thank you for your attention, and
thank you very much. Thank you very much, Professor Ekert, for a wonderful talk. Are there any questions from the audience? You can unmute yourself and ask.
Hello.
Hi.
Yeah. Hello, Professor Ekert. Thanks for the beautiful talk. I'm Somo from Indian Statistical Institute, a research fellow. I was visited in NUS in your lab. So, so just a few comments. So, just inside your room, it was written that Ekert's room enter with your own something like that. It is written just before your room. Enter your own security or something like that is written. So that comment is very funny. So I want to ask you one question, that now quantum distribution is very much required because of the source algorithm. But now publicly post-quantum algorithms are come. So I want to ask you that which way we should go or we should invest in the quantum domain, direct independent quantum domain, or in the post-quantum domain. So because lots of questions are coming that if post-quantum came, then we don't need this quantum distribution algorithm or something like that.
Right. Yeah. Thanks. So yeah, that's actually a very interesting question. So if you look at the data security, you may say quantum messed up many things. So first of all, on one hand, we have Shor's algorithm that took away security of many public key crypto systems. On the other hand, we have a quantum crypto that brings back security, but that may be not the best way for all practical purposes, because we also have a post-quantum crypto or quantum resilient or quantum resistance crypto, meaning a classical system that is resistant to quantum attack, even if you have powerful quantum computer. And as you may know, there was a competition for the best standard in post-quantum crypto that was run by NIST in the US with some kind of a backing of National Security Agency. So at the moment, we do have the winners. So those are algorithms that we believe that are going to be secure when we build quantum computers. So you may ask, and I think that's probably the essence of your question, like if we have a post-quantum crypto, so why bother with quantum crypto, right? So post-quantum would be much easier to install and it will be secure no matter what. Well, my answer is we should actually keep an eye on both quantum and post-quantum. One reason one should be doing this is that we never know whether proposed post-quantum solutions are going to be secure. In fact, we have, if you follow the whole process of selecting the best post-quantum algorithm, you would be probably amused to see that some of those that actually percolated to the very top, to a sort of shortlisted, not selected, but shortlisted, just went to the last stage, were broken, in fact, by people using classical computers, just a PC working over the weekend or so. So at least two of them were broken, and some others were shown to be maybe not as secure as we wish for. So there's lots of work in looking at the mathematics of lattices on which most of those post-quantum schemes are based. And the question is, do we have confidence that those post-quantum crypto system will last that long if some of them that we believe were pretty good until recently were broken by classical means, not even quantum computers? I think that the whole selection process tells us that we have to be a bit careful, and our confidence level is probably not too high. So there may be that they may not actually last, those post-quantum crypto systems. So therefore, it's important to keep on developing quantum crypto, but that's not the only reason. I think building hybrid crypto systems is probably just the best way to achieve both security and also a certain degree of practicality in the future. So the answer to your question is, yeah, invest in both.
Thank you. There's a question from Professor Shikano.
Hi. Yeah. Hi, Artur. Thank you so much. Very interesting talk. I have two questions on the sort of perfect randomness. One is on the sort of little bit practical question. Is that, as you maybe know, is that sort of there's no indicator on no distance on the indicator of between the sort of perfect randomness and the output randomness and randomness sequence. Is that possible to you mentioned about the last three? It's in the sort of using this biracial the Berry inequality, you can testing on that sort of perfect randomness. That's a very interesting idea. But sort of can we construct what do you think that can we construct it's that sort of indicator of the perfect randomness using this on that's a very biracial Berry inequality or just related on the quantum information tool. The second question is the much more fundamental question. Is that you on that related to that last question, your answer is that the quantum computer can prove of that perfect randomness is. That means on the unfortunately with it's the classical node or something, is that it seems to be impossible to perfect operation of quantum computer. That's why in that we need it on that quantum error correction or something. Then that's how to do that, how to prove on the perfect randomness using this quantum computer or just another kind of technique doing it. What do you think about it?
Yeah, let me try to. So your first question was whether we can use Bell inequalities to certify for genuine randomness, right?
Right.
And the answer is yes, we can, even though we can only go as far as randomness expansion, not you cannot create randomness from nothing. So that's the thing. So there's a bit of what we know is that if you have a small, whatever, just something that is random, you can expand and generate more randomness to it. We cannot just be absolutely sure. We cannot exclude this super deterministic scenario, which I mentioned. So that is an issue. But yes, a short answer is yes, we can use Bell inequalities to certify for randomness and mostly for expanding this randomness. Now, your second question, I'm not sure I got so you were asking about using noisy quantum computers, right?
Yeah.
For what? For randomness certification as well?
For any on the fault-tolerant quantum computation, even and that's we build it up fault-tolerant.
Fault-tolerant, yeah.
Yeah.
So
that's that we need on that. Quantum computer has that the noise.
Yeah, of course. So we have to go beyond the NISQ era. So in order to go into the crypto scenario, in order to play with randomness and play with security, we have to operate. Well, we'll never be perfect, of course, but we have to just implement error correction and fault tolerance. So we cannot do it without it. So that means like it's years ahead of us. It's not going to happen anytime soon.
I see. But how much do we need the cost on the how much sequences do we need it? That's the possible to answer it.
you know that there's this the threshold in fault tolerance. Yeah. So if you reach a certain level of precision,
right.
then you can scale. You'll never get perfect, but you can approach with a good cost, not exponential cost, closer and closer and closer to the. So if you specify your precision with polynomial effort, you can actually come closer to this.
I see. Okay.
Yeah.
Thank you. Yeah.
Thank you. Professor Bhupen Dev has a question.
Yeah, I'm Bhupen Dev from Secure. So I'm an experimentalist. I have some experiment-related question. Like for long-distance communication over land, yeah, the role of repeater or memory is, of course, is important. So what is the current status of those, and what is the longest distance that has been so far utilized in communication?
So I think, I don't know exactly what is the latest, but it's certainly the fact that when it comes to the land and using optical fibers, quantum repeaters would be great for extending the range. We don't have that. They require quantum memories. I think that's work in progress. I don't know. I wouldn't know necessarily. A good person to ask would be probably Nicolas Gisin, who is one of those leaders in this field. And last time I talked to him, I don't have a clear recollection of what he mentioned, but I think that it is promising and a work in progress. And here, the question of range really is dependent on some other assumptions that you have to make. For example, range may not always be the most important thing. For example, you want to operate at the telecom wavelength, right? So you want to go into 1.3, 1.5 microns with your photons, which is good for optical fibers because that you have the losses are very low, but at this frequency you have to work harder on the detection side than using some photons which are of higher frequency. So there is a trade-off here, and depending what you set up and what you do. So if you just go only on the ground, that would be of the you can go for tens of kilometers. However, another way to extend the range would be just to go via satellite, and then you have then of course has another experimental challenges, but you could see the Mishus satellite that the Chinese set up that managed to distribute on land over hundreds of kilometers, and that comes with another set of challenges. So there's not like there's not only one parameter, the distance, that are parameters related to how much data you can transmit. And the satellites, of course, come with all kinds of other problems. If you have for example, my colleagues in Singapore have a problem because it's cloudy most of the time, right? So it's not that often that you can get a window for the transmission. And then how many passes of satellite do you need over your ground station in order to accumulate enough data for the key, and so on and so forth. So I'm saying that I'm very much impressed by my colleagues on the experimental side, because they're trying to resolve those issues, and sometimes the data, there's a trade-off between the data, so that's why it's difficult to give. But you're right. So for the ground communication, the quantum repeaters is the next goal and objective.
Beijing, Shanghai, that's a land-based communication, right? And that.
Well, it can be, yes. So, but that has some stations where you can, yes, it is. But sometimes you may have a relay stations where you just simply, if you have a secure path, then you may just simply use that to relay the key later. So but that's ground-based, yes. And then the Chinese implemented the longer distances using the satellite.
Mm-hmm. Okay, thank you.
Are there any other questions? Okay. If not, then I request Professor
Hi.
Das to. Oh, I see. Sure. Yes.
Hi, I have a question. My name is Bonnie Paul. So my question is, from your slide, you mentioned somewhere that something called entropy accumulation theory. So, Professor Ekert, can you give us an overview of what is entropy accumulation theory?
Yes, so this so the question, is that when first of all, the entropy that we are, the different types of entropies, right? So the entropy that we are interested here for crypto purposes is called the min entropy, which is but then in a sort of, if you look for a large sequence of data in asymptotic limit, that can be expressed in terms of more regular, more common von Neumann entropy. Now, the question is, if you have several distributions, like you have a device that repeats itself, and you use this device many times in order to extract the key. The big question is the whole process of the key distribution, can it be sort of viewed as independent and identically distributed? So there's this IID assumption that every single event that follows one distribution is of the same nature. So it's just the system generates the second pair is generated independently from the first one, and so on and so forth, and have the same statistical characteristic. So if that were to be the case, that would be very easy to solve the problem of the total entropy that could be then based on simply by calculating individual entropy for the single pair distribution. Unfortunately, we cannot make this assumption for the key distribution. But when we make much weaker assumptions, namely that Alice and Bob read the data before they just make another distribution, then this entropy accumulation theory tells you that the entropy accumulates in a very similar way as IID, and therefore you can use the results that were developed by people making all those strong assumptions of identically independent and identically distributed pairs. You can use those results and show that essentially that reduces the case of more complicated case to IID case. So that's a very rough, not very precise, but a very sort of a rough explanation. You may want to just look it up, and it's not mathematically, it's not easy, even though if you want to know more about it, I would suggest some talks online which were given by Rote Aaron Friedman, the woman that I showed, that together with Thomas and Renato worked it out. So Rotem Aaron Friedman, and if you look up, she gave a very good lectures explaining how it all works, showing what the role it plays in the security. And she was one of the author of this entropy accumulation theorem.
Okay, sir. Thank you. Thank you, Professor.
Thank you. Are there any more questions?
Well, it looks like there's of course much more to be said, but I encourage you just to simply look up if you are interested in the security aspects and how those tools are developed in mathematical tools in particular, then what those lectures by Rotem Arnon Friedman is certainly something I would encourage you to look at. Otherwise, well, thank you very much for your questions and for having me.
Thank you, Professor Ekert. And I request Professor Das to maybe conclude the session.
Yeah, thank you, Arthur, for a great talk as always. So on behalf of all the members of our Center for Quantum Engineering, Research and Education, I'd like to express my gratitude to you for taking time out of your very busy schedule to give us such a wonderful talk. And I'm sure all of us have learned a lot. Certainly I have. And I think we look forward to more talks from you, more interactions. And we're indeed very fortunate to have you as the chair of a scientific advisory board. So we look forward to more such interactions in the future. Thank you again, Artur.
Well, thank you very much. Thank you for your kind words, and thank you. Looking forward to meeting you in person one day.